Today, I am going to solve the Marbleslides Challenge Set number 31. First, I will observe how the marbles drop. To begin, I open a new Desmos tab, since it provides a larger and scalable coordinate plane. The first element is a corner to catch falling marbles. I use the equation for an upside-down semicircle with its center at 1.25, 5.25, and a radius of 1.25. This, however, turns out to be a mistake, which I will explain later. Next, I create a cubic equation that guides the marbles from the first to the second star. I also assign names to each function for later use. For the second star, located at 3.25, 1, I construct a parabola with its vertex at that point, then compress it by multiplying the term by 2. Similarly, I create another parabola with its vertex at 5.25, 2. This parabola is upside down and stretched by a factor of 3/4. To avoid repetition, I use a cosine function to connect the third and fourth stars instead of another parabola. The final curve connects the fourth star to the fifth. Again, avoiding a parabola, I select a sigmoid curve, which produces a smooth transition from 2 up to 5. I then name each function in alphabetical order. At this stage, I need to connect all the functions smoothly using interpolation. I begin by defining a function s of x, which acts as an on-off switch. I use a sigmoid function for this purpose. Next, I define a function c of x, which combines two functions using the switching function. Here is how it works. F of x is multiplied by s of x with the switching point shifted to the right by 1.25. This ensures that f of x turns off after 1.25. The factor of 10 in front of x simply makes the switch sharper. Then I add g of x multiplied by quantity 1 minus s of x, which activates g of x after 1.25. As a result, the two functions now transition seamlessly. When I attempted to add h of x into c of x, the curve stopped continuing after 2.5. The issue was that the domain of f of x was the closed interval 0 to 2.5. That explained the cutoff. To fix this, I replaced it with a simpler function, quantity x minus 1.25 to the fourth plus 4. Then I multiplied the expression by another switching function at 2.5 and added h of x multiplied by 1 minus s of x. This successfully connected three functions. I repeated the same procedure for all functions until they were completely joined. The final step is to construct rails for the marbles. I insert an offset parametric function which takes t as input and outputs x and y coordinates. This function calculates the slope of c of x, then determines a perpendicular line at each point. By offsetting r units away, it generates both the upper and lower rails. I set the radius to 0.375. Initially, there was an intersection in the curve, so I adjusted one of the base functions to smooth it out. At this point, the marble slide is complete. I then copy the equations from Desmos into the Marbleslides Challenge Set number 31, adjust the parametric domains and the ball radius, and test the launch. At first, the rail spacing was too wide. After reducing the spacing, the design worked successfully. For completeness, I also found a simpler version of the equations that produces the same result. This concludes the construction. Thank you for watching.